guys, I am Ravi back with another video of the course Master the Concepts of Engineering Mechanics. In the earlier section, that is section 1, our last video or last lecture was about section 1.3, where we have discussed concepts of dimensional formula, law of dimensional homogeneity, dimensionless quantities. Now in this session, section 2.1, we are going with section 2.1, we are going to start the actual engineering mechanics, that is section 2, statics part, where we will be discussing the topics of introduction to statics, detailed explanation on rigid bodies, and then on forces and its representation. Statics. Actually, in engineering mechanics, we have already discussed that this subject deals with study of behavior of a body acted upon by forces. Now, when that body is at rest, then that problem solving of such conditions belong to statics. And if the body is at motion, then this belongs to dynamics part. So we can say that statics deals with equilibrium conditions of a body at rest. We have to note down that part, acted upon by forces. That is the statics part. The usage of fundamentals of these statics concepts date back to almost Babylonians and Egyptians period, where they used these concepts to build pyramids and temples. That's about introduction to statics. Now coming to basic definition and a bit of discussion on rigid bodies and forces. So coming to rigid bodies, I already discussed in the first session, section 1, that a rigid body is a hypothetical body in which distance between any two arbitrary points does not change, that is remains same on application of load. Now it means that this statement means that whatever may be the load you are applying on that body, there is neither any deformation nor any distortion, which means that there is neither change in its shape nor in its size. So that's what that means. So I said hypothetical body because such a body does not exist in reality. It is just an assumption so that we can make our problem solving simple. So this condition, this assumption of rigid body cannot be applied everywhere. This assumption can be applied in those cases where we are not concerned in strength perspective of the material, and we are concerned only in the perspective of finding its equilibrium conditions. Say it is under state of rest or on motion, or at what angle or what position it is. Such space-time relationship of the object can be determined. When we are concerned about space-time relationship of the object, specifically under the action of forces, then we can assume certain bodies as rigid bodies depending on how much is the deformation in reality. Let us see an example for that shortly in next 10-15 seconds. Now if we have to think of those things, think of an object in terms of strength perspective, then for strength based calculations we need stresses where we cannot neglect even small deflections. So that's another part. I will explain you with an example now. Now observe there, it is the situation 1 and it is a situation 2, where in these situations we are comparing a bar. Say there is a fulcrum to which we can add weights at its ends. Now before adding weights, that is situation 1, and after adding weights, this is situation 2. In reality, in engineering mechanics, we assume that even after adding weights, this bar doesn't deform, it remains straight, but which is not the actual case in reality. In reality, what happens when we add weights at the ends, it slightly bends. This, as it bends, this end to end length comes closer. This end to end distance between this rod, this end to this end. Initially, if it was L1, finally it will be L2, where L2 will be definitely less than L1. Now the point of discussion is how much less than. If say for suppose, if L1 initially the straight length is 1000 meters, if final length after, due to the bending, if the final length after the ends come closer due to the addition of weights, for suppose if length L2 in the second case is 990 or say 995 sorry, this is not meters, mm, 1000 mm, it is 995 mm, say for suppose. That means that difference in the size, difference in the initial and final lengths is just 5 mm. Compared to the length, it is 1000 mm, this 5 mm is almost negligible thing. So we can, for showing you that it is bending, I have shown this much of difference, but in actual that will be almost straight, but not straight. Due to addition of weights, there will be very slight bending. I am showing you the magnified view of bending. In originality, it will be almost straight. Only the 5 mm close, it's coming 5 mm closer means an angle of 0.5 degree or 1 degree deviations will be there from the original line. So, in such cases where deformation, I mean change in the size, we can take it as change in the length, end-to-end lengths for this situation. As long as we are concerned, what is the position of this bar, straight or tilted this side or tilted this side, of such cases, we can simply neglect such deviations. But this negligence, neglecting the deviation and considering the equilibrium conditions, whether it is staying in equilibrium due to this addition of weights or it is getting tilted out of equilibrium. So for checking such conditions, we can neglect this small deviations and consider this as a rigid body. So this thing comes under engineering mechanics. Engineering mechanics. Now, if you are going to study the strength perspective of the bar, we are not concerned completely about equilibrium conditions. That is already, that's after that stage. The next stage will be studying the strength perspective of the bar. This comes in strength of materials, where for such solid bodies, where we consider this even small deformations, and we study for due to such a deformation, due to addition of these forces or application of these forces, what are the stresses generated? Can the material take that stresses and withstand the load, or it will break, or it will bend, or it will yield? Such conditions, the strength perspective of study is done in strength of materials for deformable bodies. So in engineering mechanics, we deal with rigid bodies, and in strength of materials, we deal with solid bodies only, but we consider deformations, hence we say deformable bodies. Now, there are, apart from solids, we know that there are two other states of matter, that is liquids and gases. When we are studying equilibrium conditions of liquids and gases, they are also deformable. That study does not come in engineering mechanics or deformable on strength of materials, but that come under fluid mechanics. In which we study equilibrium conditions and other things, equilibrium conditions in specific and other things as well, some other things are there which you will come to know when we study fluid mechanics in relation to or in regard to fluids, that is liquids and gases. So that is fluid mechanics. So this is how mechanics is differentiated. For fluids and gases, it is fluid mechanics. For rigid bodies, in solids, again two types, where we ignore deformations, where we consider deformations. Where we ignore deformations, we call them rigid bodies, and we study under engineering mechanics. Where we consider deformations for strength perspectives, we study them under strength of materials. Another name for strength of materials is mechanics of solids. So mechanics of solids, fluid mechanics, engineering mechanics. These are the three parts. Okay, so that's about rigid body. Now it is force. As we already discussed, that it is any action that tends to change the state of rest or of motion of a body to which it is applied. Now we already discussed that thing. Also I showed you with a diagram or example in the section 1. Now also I have discussed that complete definition of force or complete specification is given by its characteristics, and there are three characteristics of a force. First one is its magnitude, second one is point of action, and third one is direction. It's direction of the force. And also we come across that SI unit of force is newtons. Of course CGS unit is dyne for your information, and 1 Newton equals to 10 power 5 dyne. So that's another case. Now coming to effects of forces, there can be either linear or there can be angular or both. Say there are three scenarios here. On a level ground, I have placed an object and I am applying a force in this way. So what happens for this scenario? This force tends to move this object along a straight line, which is a linear path. So when the force tends to move, and then by the term tends, I meant to say that its attitude, its objective of the force is to move the body along a linear path. For that I am using the word tends to. Now here in this scenario, if you say, if we try to pull from this point in this way, then this wheel will try to rotate about this point. That is, there it is having, for that particular instant, that particular second, when we are trying to pull it against this step, it is trying to rotate about this point. So it is having an angular effect. This force is having an angular effect on the body. Now consider another scenario where here there is a pivoted shaft to which a link is there, or mounted on a link is mounted on this shaft, and on this link again a piston or a sliding object is placed on this link. So what happens, this link can slide over, slider can slide over this link. Now when we apply torque, you will shortly know what is torque and everything. That means that when I try to rotate this link, then what happens, there a force called centrifugal force comes into play, due to which its effect will be, it will try to, that centrifugal force will try to move this object away from the center of rotation, right? So due to the that effect, centrifugal force effect, this is moving along this link away from the center. That is a linear path. Also that comes when we are trying to rotate the link. So along with this link, since this is mounted, this slider is mounted on this link, along with this link, this slider is also rotating. So at the same time it is sliding as well as it is rotating. So it is having linear motion, having angular motion. So effect of such forces, combination of one or two forces, this torque, applied torque as well as centrifugal force, is that overall, finally, as a resultant, this body is having both linear and angular effects due to that force. Right? Now coming to representation of force, say there is a body, an object placed here, a rigid body, as far as we are considering with engineering mechanics. Say there is, how to represent a force. Say for example I am applying a pulling force on this in this northeast direction. Say for example I am applying here. Now magnitude of force, there are three characters. Graphically when we draw, we represent a force graphically, it should give us all the three characters of a force. What are the three characters? Its magnitude. The magnitude is given by the length of the line segment of the force. It gives us magnitude. Say for example length we have taken is say 5 centimeters. We can scale it. Say for example for every 1 centimeter there it is 10 newtons. Then if we draw 5 centimeters, it means that there is a load of or force of 50 Newton acting on the body. Now next one is point of application of force. When we say point of application, at what point on the object it is trying to act or focused. So by the term point of application, we say that point where we can assume, I am terming assume that the force is concentrated through it or acting from it. So this is the point. I said assume, there is a difference. So I will tell you shortly. Now for now, point of application will be this, on this object. From here the force is acting. Now depending on whether it is pulling or pushing, our direction will be decided. Say for example it is pulling, this will be the direction, it is acting in this direction. Now graphically by arrow mark we can do like that, direction we can specify direction. Now if you want mathematically, how to do it? Say for example this is a reference line, Now since this is the direction, our direction mathematically can be calculated as θ1, angle, from the reference line to the leaving direction. From this point we have to note that for calculating this or measuring this angle, force should be in a leaving condition, either this side or this side. So if the force is acting along this line, this line gives us the direction in which it is acting, and it gives, arrow mark gives the sense, this direction or this direction, this way or this way. And when this is in this direction, we calculate θ1. Now for example this is downwards, sense is downwards. Then we have to, for measurement of angle at which the force is acting on the body, we cannot say again θ1. We have to, since if sense is in this way, we have to extrapolate this line to this side, and from this point with the magnitude of the force, since it is acting downwards, we have to draw a line segment this way, and we have to measure the angle from here up to this point. So this θ2 gives the direction in the second case, if the force is in the downward direction and the point of application is this, right? Now I was saying point of application is the point where a point in the body from where we can assume that force is acting. Now I said assume, I used the term assume. Why? Because in reality action of force is over certain area, so we can only talk about the effect of force in terms of pressure, because pressure is nothing but force per unit area. Force in reality does not act at a single point. If, for example, say for pulling this body, I am assuming to be a point, but actually how can we pull this or push this body? Say for example we are pulling this body. Here we attach certain object or some fixture in which we will apply some mechanism from which we will produce some lever. By pulling this, we can pull this object. We can pull this or this, depending on the direction, we can move this object. So when we are trying to pull, this total force is transferred to this total fillet or total collar or whatever it is, that mechanism. So up to this part, and in this part, that effect of that force is distributed in terms of pressure or stress. No, so here the force is not concentrated at a single point. So we cannot, in reality, we cannot say force is acting on a point. But when compared to the overall dimension, if this area over which this force is acting is negligible, then we can say consider this whole thing as a single point. So that's how it comes. And also, sensibly, without affecting the conditions of equilibrium, if we are able to assume this total thing as a point, then it is good for us, because if we are going to deal with area and then do the calculations, it will make our calculations complex. Now if we do by assuming it as a point, our calculations will be easier. So two things: one, it is not affecting the conditions of equilibrium, and two, our problem solving becomes easier. So for that reason, in most of the cases, we assume certain point from which the force acts, such that there is no effect on the equilibrium conditions. Now coming to types of forces, there can be two types broadly: point or concentrated load and distributed load. This point or concentrated load again is an assumption. In reality, it does not exist. But let me explain it with you an example. Say a shaft which is free to rotate is mounted in over bearings, and a rotor is mounted on that shaft. Now this is connected to some power system which rotates and in turn rotates this rotor, and this rotor rotates this shaft. In that way, when it is rotating, actually this has some weight, because it has some it is composed of some matter, and matter has some mass, and hence when there is mass, and as it is on earth, there is gravitational pull, so there is a weight of mg on acting on this, and this weight of this rotor is supported by this shaft. Hence we can say that weight of this rotor acts on this shaft. But we know that weight is depending on the mass, and mass is composed of matter. So this total is, everything is matter. If we zoom it, this is something like this, and this part is hollow, from where shaft goes, and above it and below it, it is a rotor where composed of matter, and every particle has some mass. So individually on every particle, this gravitational force acts. So gravitational pull on this rotor acts on this shaft along up in this length, in this zone. This is the total length of the shaft. In that zone, for this particular zone only, this weight acts. This weight is distributed from this point to this point, from this zone to this zone. So this total zone is acted upon by the gravitational pull of this rotor onto the shaft. Now when you compare this length, this zone, with the total span of the shaft, it is negligible. If this total is say some 1000 mm, this will be somewhere between some 10 or 20 mm. So 10 and 20 mm are almost negligible when compared to 1000 and 2000 mm. That is 2 meters compared to 1 meter and 2 meters shafts. 10 mm and 15 mm, 5 mm, those ranges of rotors sizes can be neglected. Hence, instead of considering everywhere, we consider that there is certain point through which we can assume that this total gravitational pull on the body can be assumed to pass, and this point is nothing but we call it as center of gravity. So this total gravitational force is assumed to pass through that point. In reality, the gravitational force acts on each and every particle, but without affecting the conditions of equilibrium, without changing the sensibly the conditions of equilibrium, we can assume that the resultant of all these particulate or individual forces together, when we see them as a total object, we can see that it acts along this point, and we call that point as center of gravity. And same thing we apply here, and we assume it to be passing through the center of gravity through this point. In that way we focus it as a point loads, and also the span over which this matter is distributed, which is acting force on this shaft, is limited, very small, negligible. So in that cases we can call it as point or concentrated loads. Now in distributed load, say for example there is a dam wall, say there, here water flow system is there, gates are there. This is a construction material of the wall. Now this side it is the downside, and it is upper side where water is filled up to the level. I am showing you this view only. In actual, this is in 3-dimensional. You can assume it to be like something like this. I am showing you. No, I am not showing you the 3-dimensional view. I am showing you just the 2-dimensional. So this wall which is there, on this wall if you observe, water is spread all across, and when water is spread all across, you cannot say that force is acting on at a single point. The force is not actually acting as it is, but its effect, we can sense its effect in terms of pressure from this level to this level. As the depth of the water increases, pressure that acts on the wall also increases. Those things, those concepts you will learn in fluid mechanics, but presently you remember that as the depth increases, the magnitude of the force or magnitude of the pressure acting on the wall increases. So this is the actual we can call it as a distributed force. In this case it is increasing. In some cases it may so happen that it is acting all across the wall, but the force is uniformly distribution. We can call that as uniformly distribution. But in this dam wall case, it is not uniformly distributed. It is varyingly distributed. In both cases, distribution is there. For example, say there is a beam on which we have placed a certain load whose span is considerable with respect to the span of the total length of the beam. So when compared to this length is also comparable. Cannot neglect it. In such case, weight of this will be acting all along this span. So up to this much span, there is a distribution of weight in terms of gravitational pull. So this will be like uniformly distributed load. This is the case of uniformly varying distributed load. This is uniform, this is varying case. So there are some other examples of distributed loads as well. For our understanding purpose, this is apt and enough. So these are the things I wanted to discuss in this class. Now one more thing I wanted to say. Since this pressure is applied on this wall, similar to this, or similar to here where I have explained, we can assume that total force effectively or resultant of the total force components can be assumed to pass through a certain point as a single force. That is an assumption, and we call that point as center of gravity. Similarly, here also there will be a center of pressure. We will know that in fluid mechanics, from where we can assume that total effect of this force is acting through that point, and the total resultant force is through this. Generally we call this hydraulic force, and this we call pressure on the entire wall as hydraulic pressure. Pressure due to water is called hydraulic pressure, right? And if the pressure is due to soil, say this is complete soil filling, and the soil is applying some pressure or force on the wall, that is called soil pressure. If it is a gas pressure, say some container or cylinders, home LPG cylinders, they are filled with liquefied petroleum gas. If that is liquid level, but if there is a certain gas, natural gas, which is not liquefied, then that gas also applies certain pressure on its walls of the cylinder. That pressure is called gas pressure. Now another can be wind pressure. So such different kinds of pressures are there depending on the source of force or source of the pressure. So this is all for this class. Now let's meet in the next class for discussing other concepts of concurrent forces. We will start discussing parallelogram law, resolution of forces, etc. in the next session. So please keep in touch for the new updates. Thank you.